All right, to graph a rational function, the first thing you need to do is find the domain restrictions. So you look at the denominator. Remember, you can't divide by 0. So you set this bottom equal to 0, solve for x, and you get that x can never equal -3. That means you're going to have a vertical line, this imaginary line, that you can never touch. You'll get infinitely close, but you'll never touch it. The next thing you need to find is the horizontal asymptote. Now this is not an absolute asymptote like the vertical one. It's just a line, a horizontal line, that shows the behavior of the y value for large values of x. So if you look at this function here, as these x's get infinitely large, the +4 and the +3 don't really matter. They're negligible. So you look at just the 2x over the x. Well, the x's will cancel, and you'll end up with y equals 2. This will be your horizontal asymptote. You'll get infinitely close to it as x goes to -infinity and as x goes to +infinity. Next, we're going to find the y-intercept. Well, all you have to do is plug in 0 for the x's and you end up with 4/3. When you find where you cross the x-axis, that means your y value is 0. So if you're setting a fraction equal to 0, it's only the top that can make it equal. So you set the top equal to 0, solve for x, and this gives you your x-intercept. So now we have our y-intercept right here, our x-intercept right here. We're in this little quadrant with these asymptotes. So just pass through the points and approach the asymptote. Well, once you get this done with your intercepts, you've only graphed 1/2 of your domain. You still have all of these x values over here. So you need to plug in some of these x values to find your y values to plot some points so you can do the same thing on that side. So I plugged in the -4 and the -5, got these two y values, plot those points, pass through the points, and approach the asymptotes. All right, next problem, number 2. Again, you start the same way. You set the bottom equal to 0 and solve for x, and that's going to give you two vertical asymptotes at ±1. So these are lines that you're going to get infinitely close to and never touch. Horizontal asymptote, well, what happens to the y value when these two x's get infinitely large? Well, the -1 will be negligible, but now we have x to the 1 divided by x to the 2. That means I'm going to have infinity times more on the bottom than I have on the top, so you're going to end up with y equals 0. Plug in a 0 for the x's to get your y-intercept, and you get a 0, so you have a point here at the origin. So the origin point is between the two vertical asymptotes. I need to know, am I going to go up here and here? Am I going to be like an upside down parabola? Am I going to come up from below and pass and go up to the right? I need to figure out how that's behaving. So we could plot -1/2 +1/2, and that would give us these points right here, and then we would know how it behaves. But let's just for a second look at our function and examine its behavior. Think about the denominator and the numerator in terms of, are they positive or negative? Well, obviously the numerator is negative when x is negative, but the bottom, x squared, would have to be smaller than 1 for the bottom to be negative. So actually this denominator is always negative between your asymptotes. So if the bottom is negative and the top is negative, which would be for these x values right here, a minus over a minus is a plus. So all of these y values have to be positive. So we know we're going up here. For the x values from 0 to the right-hand asymptote, the positive one, the bottom is the denominator is negative, but the numerator is going to be positive. That's going to make that go to -infinity here. Okay, when we're outside the asymptotes, where x squared is bigger than 1, the denominator will be positive. So for positive x values, my y values are positive. I know I'm going to be here. I chose to stick a 2 N for the x's, so that I could plot a point, pass through the point, and approach the asymptotes. You can do the same thing over here. Plug in a -2, I get the -2/3, so I pass through the point and approach the asymptotes. But remember, if you're outside your asymptotes, the bottom's a positive number. So if the top is negative, I know all of my y values will be negative. That puts me down here. You can plot as many points as you want. Just make sure you're doing your calculations correctly. Okay, number 3 and 4, you're supposed to expand using the properties of logarithms. So, properties of logarithms, remember the log is the exponent. Now, on this particular copy of your review, the print got messed up. That 3 right there was actually a subscript, and this 3 was an exponent. So we have log base 3 of 9 x cubed blob to the 5th, okay? So remember, the log is the exponent, so if I'm multiplying, I always add my exponents. So we need to see this as 9 times x cubed times blob to the 5th. So I'm going to have log base 3 of 9 plus the log base 3 of x cubed plus the log base 3 of blob to the 5th. Now the next step is to take those exponents and bring them down to the line. We also can find the real number value for this. 3 to the what equals 9, that becomes a 2. This exponent becomes a coefficient, and we get 3 times the log base 3 of x, and that 5 comes down to the line, and you get this. Now, if you know what you're doing, you can look at this original and go straight to this answer, and you'll save the time and effort to do this middle term here. Okay, number 4. Remember, if you're multiplying, you're adding the exponent, but if you're dividing, you're subtracting the power. So we're going to get the ln of each of these factors. You see the little red dots that shows multiplication. So we're going to get the ln of 4 plus the ln of x squared plus the ln of y cubed, and then minus the ln of this blob squared. But these exponents can come down to the line as multipliers. So we end up with plain old ln of 4, positive 2 ln of x, positive 3 ln of y, and then negative 2 ln of z plus 5. Now for number 5, we're going backwards. So remember, if the ln is positive, it's multiplication. If it's negative, it's division. And if there's a number in front of the ln, we bring that up and make that an exponent. So we have the ln of just one big nasty, right? So the ln of 2 is positive. That puts 2 in the numerator. The next one is negative, and 4 is the exponent. So I'm going to put 2x plus 1 to the 4th in the denominator right here. And I'm going to put, this is positive, so I'm going to put y minus 1 to the 3rd in the numerator, and then z in the denominator. So positives, all of those guys are in the numerator, all the negatives are in the denominator. Number 6 and 7, you're supposed to evaluate without a calculator. Now, again, the formatting got messed up. This should be e to the 4th power. Something happened in the transfer of the file here. So there's numerous ways to do this particular problem, number 6, based on these properties. But I choose to say that the ln of e to the power is just the power. So this ends up being 3 times 4 minus 8 times, this is e to the 1. So that's a 1. So 12 minus 8 gives me a 4. Another way to look at it is to condense these logarithms. I didn't write this down, but you can take this 3 and make it an exponent. You'd get the ln of 3 to the 12 minus, bring that 8 up, the ln of e to the 8th. If you condense them, it's division. So you have the ln of e to the 12 divided by e to the 8, which leaves you with e to the 4. And the ln of e to the 4 is just 4. Okay, number 7. 5 to the what is 75. There is no rational answer for that. Same thing with log base 5 of 3. So what we're going to do is use this subtraction sign and condense the logarithms. So it would be log base 5 of 75 divided by 3 because of the minus sign. Well, 75 divided by 3 is 25. 5 to the what equals 25, and you get a 2. Okay, solving equations, and we're going to do this without a calculator. So obviously the numbering is wrong on this copy. Sorry about that. Number 8. We have a log on the left and a log on the right and just a number here. So what we want to do is get our logs both on the same side of the equal sign and condense them. So I'm going to subtract this log from both sides, which gives me this. Subtraction is division. Now I have this basic logarithmic equation. I'm going to rewrite it as an exponential. The base is 2, the log equals the exponent, and the 2 to the 1 is going to give me this thing right here. So this is a simple equation to solve. Multiply both sides by the denominator, distribute your 2, get your x's together, get them alone, and you get x equals negative 2. Now you always have to check logarithmic equations because you can't take the log of a negative number. So we're going to take that negative 2, plug it in right here, and see right off the bat that this is no solution. Number 9, again, we have logs on both sides of the equal sign, but we see that everything is an ln. So what we're going to do is condense where we can, and if we have the ln of this rational equals the ln of 3, then the arguments of our logarithms must be equal to each other. Simple equation again, multiply away your denominator, distribute the 3, collect your x's on one side, and get all your numbers on the other, do your division, and again with x equals negative 6, when we check it, we see that we get the ln of a negative number, so no solution again. Sorry, I know it's boring. Number 10, log base 3 on the left with just a whole number on the right. So I'm going to condense the left-hand side of this equation, and now I have just a basic logarithmic equation here. 3 is the base, 2 is the power, that gives me a 9 equals the x times the x minus 8. So this is my new equation. I'm going to distribute this x, pull the 9 over, factor this guy. I get 2 answers. I'm going to take both of those answers and plug them in. Plugging in the 9 gives me the log of a positive and the log of a positive, so that one works. Plugging in the negative 1, I get no solution for that, so my answer is just x equals 9. For number 11, this is an exponential equation, but it works kind of the same way. If I take the log of this base on both sides of the equal sign, this is one way to do it. There's another way. I'll write it down in a second. But if I take the log with this base, both sides of the equal sign, I have this right here. Now, log of anything raised to a power brings the power down to the line, and the log base 4 of 4 just gives me 1 times the thing out front. Or log base 4 of 4 to the power is just the power. It's one way to do that. Over here, 4 to the what equals 8. Obviously, that's not perfect, but both 4 and 8 have a like base of 2. So 4 is 2 squared, so I get 2 to the 2 times something equals 2 to the third. So 2 times something equals 3. That means that logarithm is equal to 3/2. I know that's confusing, but you got to get used to changing your base, right? You can look at this as a change of base problem. I chose to use log base 2. Log base 2 of 4 is in the denominator. Log base 2 of 8 is in the numerator. and I get 3/2 as my answer. So that's one way to do it. I'm going to work this problem a separate way in just a second that might be easier for you to understand. But once I take log base 4 of both sides, I get this equation. Just add 2 to both sides and get a common denominator, and you get the answer. So let's try this a different way. I'm going to do this in blue so we can keep them separate. So 4 is 2 squared. 8 is 2 cubed. So now I have 2 to the 2x minus 4 equals 2 to the 3. So if the bases are the same, then the powers must be the same. And I get 2x, add 4 to both sides, x equals 7 over 2. Booyah. Good luck, guys.